Okay, yeah, definitely. Okay, yeah. Well, no, no. Yeah, and definitely I'll say this now. Highly encourage questions if you guys have them. Um, Definitely encourage, and I hope I'm speaking for the rest of the presenters over the coming days. This is to be a conversation, not just one person up here speaking. And again, I hope to learn as much from you during this week through conversations at breaks, at lunches, etc. So again, John and Perry asked me to present a high-level overview of fundamentals of remote sensing. For some of you, this might be a review. For some of you, this might be a refresher. For some of you, this may be new. So I'm not going to spend too much, but I think it'll be a good foundation for the rest of the week. So please, Taylor. So we are used to taking pictures. We do it every day. That is one form of remote sensing. We use these really handy computers that we have in our pockets, and we typically take pictures in the visible spectrum, the red, green, and blue. And a lot of different platforms do the same thing. They just do it with more advanced instruments. It's the same concept, only they're capturing different bands, if you will. And what I hope to discuss in this is one, talk about satellites, sensors, some of the nuances that are involved with both of those terms, talk about some of the satellite data processing levels, which is really important because when NASA or when the Argentinian Space Agency sends up their satellites and they collect the data, they're not typically giving that information at the raw level. There's some processing that it gets involved in that so that you can take it and do analysis with it. You don't need to do the heavy lifting to get to the point to do that analysis. And that's one of the things I'm hoping to give to you today in the tools is the analysis ready data. And I hope to give it to you in a way that it's very easy to use in platforms that I'll be discussing later. We're going to touch briefly upon projections and coordinate systems. A lot of it is jargon and it's very nuanced, but I do think I should touch upon it at least so that you have some idea of the terminology, because it is important when you start working within different areas of interest to know about those. And then it's really important to know about the advantages, but as well as the disadvantages of remote sensing. So Taylor, if you can go to the next slide. So we use different platforms. I think everybody uses their phones every day. If you can go to the slide 3. Great, thank you. So every day we take pictures of our friends, we take pictures of places, things, animals. It's probably the most common relationship we have with remote sensing is with our phones, our computers that are in our pockets. But NASA uses, as well as the Argentinian Space Agency, as well as the Japanese Space Agency, as well as all the different space agencies, they primarily use satellite, so space-based platforms. But it's also very common, NASA does this, other organizations to use aerial platforms. So from drones or from planes, that is becoming much more ubiquitous now with drone technology. I'm sure you're all familiar with that, or you know colleagues or friends maybe use it as a hobby, maybe they use it professionally, but that's becoming very commonplace, especially when you start getting into more of the precision aspects. So if you're looking at, say, agriculture, and you need very fine-grained, very high precision remote sensing, that's when you start using drone imagery. I'm not going to be discussing that too much today because I'm going to be focused more on the space-based platforms. But just to know that, I don't know what this is. Oh, yeah, this is, anyway. But just to know that these are all kind of tools in our toolkit, so to speak. And all of them are valid. But again, I'm going to focus the rest of my presentation today more on the space-based platforms. But we would be nothing, anything we do with space or from space is absolutely critically important with the ground element. So to have somebody there to validate what you're seeing from space is so important. And all the different space agencies if it's here in Argentina, if it's in Japan, if it's in the French or the Brazilians, you name it, all of them are spending a lot of time with validating and also calibrating the instruments that are up there so that when you get that data to turn into some useful information to make a decision on, it's something that you can trust and you have a level of confidence that what you're using is accurate. So it's absolutely vital to have that ground base to it, but that is all behind the scenes. But I can tell you that a lot of effort by all these agencies is spent in the field on campaigns, working to validate a lot of the data that's coming down. So next slide. So very briefly, there's a lot of different ways that we collect or observe the energy that is coming from our planet from space. Some of that is, well, the majority of it is coming from the sun, and it's being reflected or scattered, or it's being emitted in the form of thermal heat. Maybe you can think of a warm body or a volcano that's emitting energy. So these are different ways that we can collect that using space-based platforms. So again, it's either radiation coming from space, it's either reflected, it's absorbed, and it's also emitted. And the satellites that are up there are carrying instruments that are measuring all the different light energy that's being reflected or emitted from the atmosphere to the biosphere, so all plants and life, to the lithosphere, all the geologic formations, and then also the hydrosphere, which I think probably most of you are concerned about, if it's oceans, rivers, riparian areas, lakes, etc. And so NASA uses all these different instruments to measure the height, temperature, the moisture content, soil moisture content, for nearly every feature of the Earth, from the atmosphere to the hydrosphere, to the lithosphere, to the biosphere. And NASA, as well as many, many other space agencies, for decades, have been collecting this data to create a time series, a record that we can all use and hopefully contribute to our scientific understanding of how things are changing on our planet. If we can't observe it consistently over time, we don't really know how things are changing. So that's one of the great advantages that a lot of the space agencies have given, is this long-term record. Next slide. So this is a infogram, a diagram showing the electromagnetic spectrum. Many of you have probably seen this in some class or somewhere before, but this is just to say that everything that we see, that everything, your clothes that are being reflected, your backpack, the light that's being emitted from these incandescent light bulbs, everything we're seeing is right in here. But the instruments that we're sending up in space are collecting this whole range, this whole spectrum. There are spacecraft that NASA has launched that are observing the sun every 15 minutes. And they're collecting primarily X-ray, ultraviolet, infrared, and microwave. A lot of the Earth observing satellites, those that I will be primarily discussing today, are collecting things typically from the visible to radio, so more on the longer wavelength. But they're all contributing to our understanding, because the energy coming from the sun ultimately is going to drive all of the processes on Earth. And so NASA is collecting this information, and even though we cannot see this whole spectrum, we have the instruments to be able to observe it. Next slide. And so the chemistry of these different surfaces, if it's trees or rocks or buildings or anything else, they reflect light in different ways. And that's how we're able to identify the spectrum of, say, some grass versus a house versus a building, etc. And we're able to do that by collecting these different spectra in different bands. It could be in the RGB, the red, green, and blue bands. which we're typically seeing right now with our own eyes, or the light that's collected with our cameras. It's the same thing. But we can also collect those 3 bands. We can expand that out into the near infrared, into the shortwave infrared, into the thermal infrared. And if you think about when you capture an image, it could be with your phone or it could be with an advanced instrument. It's capturing all those different bands. So think of just like a sandwich that you're stacking up. It's the same dimension, it's the same area, but it's being captured in these different spectra. And when you start plotting that out, you start seeing similarities in the different signatures. So snow and ice and clouds are very, very reflective, especially in the visible, which is what we're seeing here. And you can see how water is more reflective in the blue and the green bands, but starts dropping off in the red. It starts being more absorbed and less reflective in the red and then the near infrared. So it's much more absorbent in those bands. So understanding how these different surfaces, and particularly the chemistry of these surfaces, is causing them to reflect light differently, helps us identify and distinguish between the different land cover types or water types that we're looking at. So this graph on the left is just comparing that relationship between that percent reflectance and the reflective wavelengths of different components of the Earth. And I should have said this already, but all of the materials that I'm presenting on today, you have links to, and they've been translated into Spanish. So you can go back and maybe, English is not your first language, but you have access to all of this in Spanish. And it's already, you have a link for it on the agenda. So I just wanted to let you know that. Next slide. Very briefly, this is talking about how light interacts with vegetation, particularly healthy vegetation or non-healthy vegetation. So certain pigments in plant leaves, chlorophyll, strongly absorb wavelengths in the visible red spectrum, especially. And that's for healthy vegetation. So any tree, grass, you name it. If it's healthy, like the jacaranda trees or all the trees that are now springtime I got to tell you, I'm coming from like fall and winter, and it's really nice being here because it's a beautiful weather, and it's so nice being back in spring because I love jacaranda trees and it's really nice walking around. And so seeing that those healthy trees, they are strongly absorbent in that red band, and they're very reflective in the near infrared band. And those are some of the ways that we can distinguish vegetation from non-vegetation, and also healthy vegetation from non-healthy vegetation. And it's really useful as well if you want to look at seasonal patterns, if you're looking at phenology. So if you're interested in agriculture, when you plant and when things green up and then when they senesce, or if you're looking at seasonal changes in natural forests, if you want to see if they're deciduous forests and they have a peak in greenness and then a senescence when they stop photosynthesizing, you can use these spectral bands to be able to observe that throughout the season. And I'll be showcasing some of those examples in the tools I'll be speaking to later, but just to plant that seed in your head now. And since we cannot see the near infrared, but we do have the instruments to do it. And those instruments, again, could be literally on they could be on a tractor if you're a farmer. A lot of the advanced agriculture now is building these instruments onto the equipment so they can observe it in the field at the time of working. A lot of people are using drones now. I think I talked about that, as well as aerial platforms or space-based platforms. But these are all different ways to observe that spectra that we cannot see with our own eyes. Next slide. And so I think a lot of you might be biased that maybe water is more of your focus of interest. And there is a lot of research, applied research, as well as basic research that's going into building algorithms to be able to assess water quality, sedimentation, et cetera. which my colleagues will be discussing later this week. This is just saying basically the longer visible wavelengths, think of your reds and your near infrared that I just spoke to, they are absorbed more by water than the blue and the green, which is why typically when we see water, those are being reflected just because the chemistry of that water is more reflective in those bands. And so, yeah, satellites provide the capability to map optically active components of the upper water column in both the inland, so your lakes, your rivers, et cetera, as well as your near shore water. So anything right off the coast. So think of the estuary for the La Plata Basin. I know a lot of research is going into that, as well as all the coastlines that you have on this amazing continent. Next slide. And then there's also a lot of folks that are interested in atmospheric chemistry. And there are a lot of NASA missions, but also a lot of European missions as well, spacecraft that are observing just the atmospheric column. And that could be everything from carbon dioxide to ozone, and as well as aerosols and how aerosols are being spread throughout the planet, both from anthropogenic as well as natural. It could be through dust storms, et cetera. So these are being observed every single day globally, and they have been for decades. And the only way we can make informed decisions is to have that consistent record and to keep those data points being stacked up over a long period of time. And that's how we can understand the changes that are going on. So next slide. This is an animation from 2017 until present. And it's basically showing how the Earth is breathing and growing. You can see right now it's going into the spring in the Northern Hemisphere. And as it starts going into the fall and into the winter, you can see how the green starts traveling back up and down the tropics. This is very much evident in Africa, as you can see the green up seasonally, as well as in the Northern Hemisphere, especially the great boreal forests that trap a lot of the carbon. You can see them greening up, especially as the spring hits. And then if you look at the oceans too, there's many missions that NASA has that are monitoring chlorophyll levels globally on the ocean. The ocean gives us a lot of the oxygen that we breathe. Actually, I don't know the exact percentage, but it is a lot. And understanding where that chlorophyll is and how it's changing and how much it's contributing is vitally important. And this time series starts in 2017, but these records go back much more before that. And all of you have access to this data. This is NASA. I think John made a good point earlier when he got up here, and he emphasized that NASA is promoting open science. So any of the data that's collected, any of the imagery that's being collected, all of it is open access or open source. And so it's publicly available. You do need an account. It's free, but you can get any of this and you can work with it on your own GIS or your own image processing software. But NASA is committed to open science. And that's one of the big pushes that has been, and you're going to hear more about this, I think, too. The data has always been publicly available, but there's now a big push to make people aware that they do have access to this. And so anyway, all of this is yours for the taking. Next slide. So I'm going to briefly go and touch upon satellites and sensors and distinguish some of the terminology involved with both of those. So next slide. So this is an image of a satellite that was launched 2 years ago. It's Landsat 9. It's the 9th mission in a mission that's been going on for 50 years. This year is the 50th anniversary of the Landsat mission. Landsat stands for Land Satellite. And it's a collaboration between two different United States government agencies. That's the Geological Survey and NASA. And ever since 1972, when this mission was launched, those agencies have been working very closely together to make sure that that data is, one, that the spacecraft is flying in its orbit correctly, and that all the data is coming down and it's all being shared with the public. And so this is what we call the spacecraft bus. Any spacecraft, just the body of the spacecraft we refer to as bus. And then one of the instruments is the operational land imager. This views things in the optical realm. And then we have the thermal infrared sensor. So this is sensing heat from the surface of the planet. So if you're interested in assessing, say, urban heat islands, which is a big problem in a lot of urban areas across the planet, you can do that with a very good resolution compared to other products that are offered. So this is just some terminology. Next slide. And some of the things I'm going to touch upon briefly in the next probably 10 to 15 minutes. I'm going to talk about satellite orbits. I'm going to talk about the energy source for how the imagery is collected. I'm going to talk about the solar and terrestrial spectra. I'm going to talk about how the technique for gathering that data is done, and resolution type, which is really important dependent on the application that you're trying to use it for, and then ultimately the application. So next slide. So this next slide is showing you a mission from, it's a joint mission. This is GOES East and West. This is a joint mission between two other US government agencies. This is the National Oceanic and Atmospheric Administration, otherwise called NOAA. They're the ones that have all of the meteorological satellites that the United States puts into space. And they're collecting, their orbit is geostationary, which means it is in orbit at the same rate as the rotation of the planet. So it's always looking at the same place. So it's always collecting weather at that same place 24/7, day and night. And it's doing that, I believe it's every 5 to 10 minutes, it's collecting this information. And that's, not only is it collecting it in that time frame, but the instruments that they're putting on have such a advanced radiometric resolution that it helps improve weather models. So if you're interested in hurricanes or cyclones, depending on how you like to refer to them as, this is all contributing to our understanding of meteorological phenomenon. But the important thing here is the orbit is roughly 36,000 kilometers. And that distance, which is also where telecommunication satellites typically are, they're in that orbit there. And so they're always able to, their orbit is matching the rotation of the planet. And that's how they're able to relay telecommunications whenever you want to call somebody, or if they are collecting information on the weather. So that is, and it's, again, multiple observations a day. It's way more than that. With actually just last week, NOAA and NASA just launched the latest, actually this is going to be a polar orbiting spacecraft, but it's contributing to this. And I'm about to talk to you about polar orbiting spacecraft, but it's contributing to our understanding of weather. So next slide. So we just talked about geostationary. This next slide is showing an example of low Earth orbit. This is where the majority of Earth observing satellites are. The reason why we put them in low Earth orbit is because we can collect a lot more high resolution imagery. And we can also, because it's in low Earth orbit, you can typically have, I think it's 16 orbits a day if they're polar orbiting. So you can gather data globally. And so you're not relying on just one part of the Earth that you're observing all the time. So even though the extent or the swath of that area that you're collecting, it might not be as big, but because they're constantly in orbit collecting, you can get, depending on the spacecraft, you can have a global, observations every day, or in some cases, it might take up to 2 weeks. So These are orbiting relative to the Earth, and they're less frequent measurements. So that geostationary orbit, they might be collecting data of the same place every 10 minutes. With this, like I said, you might have data collected globally every 1 to 2 days, or again, it might be 2 weeks. It just depends on the orbit. And some of these orbits in low Earth orbit are polar, some of them are equatorial, and some of them are at an inclination, like the International Space Station, which I don't know if there's been any Argentinian astronauts. I would like to know. I hope I can find out soon, but I want to say that there have been. But the orbit of that International Space Station is not a polar orbit. It's at an inclination that it goes, I think it's roughly 40 degrees north and south latitude. So some examples of this are the polar orbit, are the Landsat mission that I referred to earlier. And then some non-polar ones are the GPM mission, which you're going to hear about. I believe Dr. Lakshmi is going to be speaking about that, I think tomorrow. And then also the International Space Station. Next slide. So this is just repeating what I just said about the polar orbiting. And I'm also going to go into a little bit of detail on a sun synchronous orbit and why that's important. So the good thing about a polar orbit is you're getting global coverage. And even though it says polar, it doesn't necessarily have to go right over the poles. It can be off in inclination by 20 degrees, and you're still going to be capturing a global observations. So it doesn't have to go directly over the polar, but as long as you understand the concept that that is its general orbit. And the benefit of the global orbit is, one, it does capture global observations, global data. And again, it can, depending on how big the swath is, you can be collecting data daily for a global, or it could be more than that. And the important thing about the sun synchronous orbit is anytime you, and I'm sure a lot of you have done this in your own professional lives, but if you're going to collect data on something, you want it to be consistent, right? You want it to be at the same time so that you're constraining anything that might be contributing to that. So in a sun synchronous orbit, it's passing over the same part of the planet at the same time. So you can have a consistent observation, even if it's a week later or if it's 2 weeks later, it's going to be passing over that same part of the planet at that same time, so that you can have consistent objective observations over time. So that's a benefit of sun synchronous orbit. And a lot of the missions that I'll be discussing later today have a sun synchronous orbit. Next slide. And I talked briefly about this. The passive sensors are using the sun as its main source of energy. You're basically collecting anything that's being reflected or scattered or emitted from the Earth's surface or from the atmosphere. And those are passive sensors. They're basically just collecting anything that's being reflected from the atmosphere or from the surface. So they're using ultimately the sun as the source of energy. And I'll be giving examples of those later. And then next slide. And then the difference between a passive and an active sensor is an active sensor has its own source of energy. That could be microwaves. It could be LiDAR in terms of light detection and ranging. This is a different instrument that's used to measure topographic profiles of both oceans or lakes or ice sheets in the poles, or even canopy heights of forests, if you wanted to do some type of carbon sequestration analysis. So these are different examples of active sensors. So they're basically using their own source of energy to pulse light. It could be microwaves. It could be infrared light, which is what a lot of LiDAR uses, a lot of LiDAR instruments. But they're using their own source of energy instead of relying on the sun to reflect that energy. And some of the things I'll be talking about later today, you do use active sensors for some of the tools that I'll be demonstrating later. Any questions by chance? Great. And these are just different examples of missions and then some of the instruments that are using those that I already mentioned. Okay, next slide. And now we're going to start talking about the nuances of resolution. Because depending on what type of analysis you're doing, you are going to be limited to different types of resolution. And the example I'm showing here is a limitation, or not a limitation, but just generally a spectral resolution. And so what spectral resolution is showing is the number of bands that you're collecting and also the width of those bands. So we talked about the electromagnetic spectrum, and we talked about how we can only see in the visible, but the instruments that we're using are able to collect throughout that entire spectrum. And that resolution is basically saying what part of that spectra that you're collecting. So let's just refer to it as one band. Let's say we're going to make a sandwich of bands, and we can make that sandwich as big or as small as we want. Maybe we just want 3 bands. Maybe we want near infrared, short wave infrared, and maybe red. And so maybe there's only 3 bands in that sandwich. But if we wanted a more robust multispectral resolution, we would have more bands within that spectrum. And also the width of those bands will also be dependent and determining the resolution of the spectral resolution. So this is an example of multispectral. This is the vast majority of all of NASA's missions are multispectral. But in 2 years, NASA will be launching a hyperspectral instrument. And I'm gonna circle back to this idea soon in terms of how the computing power needs to be improved or has been improved, because when that mission launches, the first year of that mission collecting hyperspectral will be more data than NASA has collected in the history of the agency for all of the missions. So that's how things are about to change. And that's how we need the computing power to be able to handle that volume of data and to make it, again, useful. We don't just want the data, we want to be able to make decisions from it. So how can we turn that into information that can get to scientists and decision makers? So that's the difference between the spectral resolution and a multispectral versus hyperspectral. And next slide. And spatial resolution, a good example of this is the 3 images in the bottom right of the screen. We can see a much, I think this is quite intuitive, but we can see a very high resolution. This is I believe, a 1 meter digital globe, 1 to 4 meter. And then we have I think this is Landsat here, and then MODIS. And so these are just different ways of looking at the same extent, the same area of the planet using different instruments. I think that's very intuitive. I'm sure we've all used antiquated software that might not be as high resolution. Maybe it's on our phones, maybe it's on our laptops from many years ago, but that's what this is referring to. So it's really the pixels, actual dimensions of the pixels as they're measuring on the ground. And that's what we're referring to spatial resolution. And a lot of times people think, oh, it's always good to have the highest spatial resolution. Well, that's not always the case. And a lot of times, depending on the ability to process that data, it's not the most appropriate. But for some applications, it's definitely appropriate. So it's really case dependent. But this is just an example of spatial resolution. Next slide. And this is contrasting spatial resolution versus spatial extent. So typically they are inverse to each other. So typically the higher the spatial resolution, the smaller the pixel, the finer grain, the more clear that image is, less area is being covered. So this is a higher spatial resolution. I'm actually from this part of California. And so this is a Landsat image. And this is a much higher spatial resolution than a MODIS instrument, which is on a different a spacecraft. It's on 2 different spacecraft, actually, same instrument. But you can see that the extent of what it's able to capture, let's say it's just one picture, one image, you can see that there's quite a contrast. And that's why the ability of this instrument on that spacecraft can capture global observations everywhere on the planet in 1 to 2 days, where this instrument takes 16 days to come back to this one spot on the planet, just because its extent is much smaller. But that's what we're talking to when referring to resolution versus extent. Okay, next slide. And I've got two more resolution topics I want to cover. One is temporal, and that's just the revisit time. So let's say we're in Buenos Aires today. I'm really happy being with you all. And so any instrument on one of these spacecrafts will observe this one spot on the planet, and it will take how many days to come back and observe this one spot on the planet? It could be less than a day. It could be 16 days. Maybe it's 21 days. And so that's the temporal resolution. What's the repeat time? And as I said, there's an inverse for the typically from spatial resolution and temporal resolution. And sometimes if you're looking at phenomena such as maybe the growing season or agriculture, maybe you really want that high temporal resolution. So you have frequent repeat times to see when things are greening up and then flowering and then fruiting and then going into senescence. So maybe you really want that trade-off for the higher temporal, or maybe the application is more for higher spatial resolution. So you're willing to sacrifice that daily repeat to get maybe something every 2 weeks, per se. So there's always a trade-off, and it's one of the things I'm hoping to plant that seed. There's always going to be a trade-off between all these different resolutions. Next slide. And then finally, these are the radiometric resolution. And this just refers to the number of bits in any pixel. It could be a 4-bit, a 6-bit, an 8-bit, a 12-bit. It's just how much energy, how much radiance that one pixel is able to gather. And so if you have a 12-bit sensor, which is on the Landsat OLI, which is one of the most recent instruments, the Landsat. This is on the Landsat 8 mission, and Landsat 9 has Landsat OLI 2. But that 12-bit sensor is able to capture a lot more of the radiant energy than something that has, say, and this is a good example of this, the 2-bit is only able to capture, let's say in the panchromatic spectrum, only 4 tones. Whereas if you have this 8-bit, you can have up to 256 values, digital numbers, that you can store values for in every pixel. And this is for 8-bit. This is, Landsat 8 is up to 12-bit. So it just allows you to have a finer grain on how much energy or radiance you're able to collect per pixel. And that's what radiometric resolution is referring to. Next slide. So I'm going to go briefly through processing levels. So once the spacecraft is launched, and once the data has been gathered, and then it's been sent back down to NASA, they need to do processing so that it can get into our hands to do the science with it. And it's possible that maybe you really want to work with the level 0 data or level 1 data, but typically what most scientists favor is using higher levels of processing, which are more analysis ready. So they do all of the work in terms of radiometrically correcting and geometrically correcting. So it's georeference to a place on the planet. All of that's done so that you can take some of these higher level products and actually just do work with it, do the analysis, instead of having to do any of that pre-processing. And it's good that you know that, because if you are not already, hopefully you'll be starting to work with some of these data sets, and you'll know intuitively that, you probably want to start with like a level 2 or level 3 product. And once you start getting to level 4 products and behind and above, those are typically more modeled products. So they're taking the observations and they're doing some modeling to be able to derive a product that's giving you some biophysical or geophysical product that you can understand and do some analysis with. So the level 3 and 4 data or products, they are definitely the easiest to use, and we call them analysis ready, which is what they are. But maybe, I don't know, maybe you find a situation in which maybe you need to use, the level 1 or 2 products, which could happen. But just know that the way that NASA serves the data, it comes in these different products. So next slide. And I'm going to go very briefly through these next slides. So anybody seen an image of this before, the geoid? Yeah, okay, I've seen some heads nod. So this is a construct of what the mean sea level would look like on the planet reflecting of all the different topography, all of the different mountains, everything else. And if there were no effects from tides from the moon or from any meteorological phenomena, so like winds blowing oceans around. If everything were smooth and all the oceans were connected, so they were all basically at the same level, and it's also reflecting all the different gravity on the planet caused by ice sheets and mountains and everything else. This would be a replica of what the Earth would look like at mean sea level. And this is what we refer to as the geoid. It's a hypothetical shape, but what it does is, next slide, it helps us to start making sense as we map the planet, because this is one thing, this hypothetical construct, but we want to actually be able to create accurate maps when we work with the data. And the only way we can do that is, well, there's other ways, but the way that everybody does it is to fit a spheroid to that geoid. And that spheroid is very relative. It can be relative to anywhere on the planet. So if you wanted to map an area here in Buenos Aires, you would probably use a spheroid that is associated with a specific datum. And that datum, think of datum as the singular for data. So think of datum as one location where you have complete accuracy of location at that one spot. And so that helps you actually create accurate maps. Maybe you don't want a map of, say, one location. What if you wanted a global map? What if you were studying, there's a lot of people at NASA, or just a lot of people in general, that are studying global phenomena. I think of climatologists that are studying global phenomenon. They would be using a coordinate system, but it would be based on a datum at the center of this geoid, because they're looking at it from a global perspective. But a lot of people, if you're trying to map, say, a river basin, or if you're trying to map a city, you'd be taking a very specific spheroid to one datum that you know that's very georeferenced. And then that way, when you build your map around that, that projection would be very accurate. And that's why we use the spheroid with the geoid to be able to construct those maps. No spheroid is a perfect fit. So many different approximations are used. And each approximation will fit one part of the Earth's surface better than others. And then I think I mentioned already that they use that datum as a point. So next slide. And then let's see. Okay, I think I already mentioned this. Because of the irregular shape of the planet, the use of datums is necessary to portray spatial data as accurately as possible. This is an example of a datum that is appropriate for the United States, or I should say North America, so northern Mexico and Canada. But there's many different datums. This is the NAD 83 datum. So they created this back in 1983. I think they're actually, the Geological Survey is about to update this, I think this year or next year, with a new datum. But North America, and for a lot of people that are studying the United States and this part of the country, the entirety, we've been using this same datum for 29 years. So next slide, 39 years, I'm sorry. And then coordinate reference systems. So reference systems are based off of the spheroid. And all spatial data needs to be georeferenced to a fixed point. Think of when I talked about the levels of processing that folks do before the data is given or served to you. It needs to be, one, radiometrically corrected, but also needs to be georeferenced so that you have confidence that the area of the observation, the imagery that you're getting, is accurate. It's actually been georeferenced. It's been mapped specifically to that part of the planet. And so that's how we use projected coordinate systems. So when we pair a data point or pixel with a specific location on the ground, that requires a coordinate reference system. And the two types that we use are geographic and projected. And next slide. So a geographic, I think, as I mentioned before, is going to use the datum at the center of the geoid. And that's going to allow you to have an accurate map of the planet. So if you're looking at a global phenomenon, you would want to use a geographic coordinate system. Some of the benefits are it is appropriate for the planet, planetary analysis, and it's good for data with a large spatial extent. So if you're looking at maybe a hemisphere, actually both hemispheres, that would be a good one. A con is it's not accurate for very exact locations. So if you're looking at, say, the North Pole, or if you're looking at Buenos Aires, it's not going to be as accurate because its intention is to be a global coordinate system. And the typical reference system for the geographic is the WGS 84. That stands for World Geodetic Survey, 1984. So next slide. And then these are types of ways of a projected coordinate system. And all that is really trying to do is take a sphere and trying to put it in a way either into a column or some way of spreading out that sphere onto a planar surface. And there's many, many, many different ways that folks have come up to be able to do this. These are a few examples. And each of those ways of taking a sphere and making it flat onto a plane uses a different projected coordinate system. And each projected coordinate system is more appropriate depending on what you're trying to do. If you're trying to navigate, say in the oceans, to go from one continent to another, you would definitely want to use one coordinate system over another because it's going to maintain the direction. Whereas others are going to maintain the distance better. So it's a trade-off. So again, like everything, it depends, but it really depends on what the application that you're trying to use it for. So some of the benefits of a projected coordinate system is it's really good for specific locations. So for, if you're looking at the South Pole or for a specific national park, or if you're looking at a specific country, or if you're looking at a specific city, it's very appropriate to use a projected coordinate system. Some of the cons, the disadvantages are the accuracy is skewed if you're looking is skewed to one specific location. And it's not useful for data with a large spatial extent. So it's not appropriate for, say, a global extent. So next slide. And then these are just different examples of how one can take different parts of the planet and then be able to flatten them onto a plane. And all of the imagery that NASA provides is dealing with this. So you don't necessarily are thinking about it because it's being given to you in some of these either geographic or projected coordinate systems. But it's really important that in the back of your head that you're aware that it is being given to you in these either geographic or projected coordinate systems. So I think I'm going to leave it there and go on. And then I'm going to quickly go through advantages and disadvantages of remote sensing. So this is an animation. One of the things that NASA is really focused on right now is instead of looking at just the atmosphere or just the biosphere, all the living life, either in the oceans or on Earth, or the soil moisture for agriculture or for precipitation, which is all being collected through different instruments. Clouds are very important. Understanding Earth's radiation budgets, how much energy is coming and going. So all of this from winds to sea surface currents, sea surface temperature, instead of looking at all of these individually, NASA is really taking a system of systems approach. How are these all interacting for one, Earth's budget, radiation budget, but also for life on the planet, for life in the ocean, the weather, the climates, how are all these interacting? And that is a huge emphasis of what NASA is currently doing. And so I put this up there just so you understand that one, NASA is collecting data and has been for many decades, but also how are they integrating all this to provide accurate and action-based decisions that we can use from this. So next slide. So So some of the advantages of remote sensing are the ground-based measurements are probably going to be the most accurate anywhere you have. If it's temperature, precipitation, soil moisture, stream flow, any of that. But you'll always be limited to those exact locations. And you can interpolate based on the network of gauges, stations that you have. But there's certain parts of the world where you don't have as robust of a network. And so one of the advantages of remote sensing is it can fill in all those gaps. And it might not be as accurate as that one exact location, but it does give you a global coverage. And that's a huge advantage. Another is it provides consistent observations. I told you about the sun synchronous time. So it's observing the same spot on the planet at the same time. So if you want to look seasonally how things are staying the same or changing, having that consistency helps to do that, as well as that long time record. And it provides continuous monitoring of the planet. And it helps to integrate both the ground measurements, that's surface-based, as well as from the space-based, to provide gridded, frequent information for water resources as well as data parameters. And another great thing, and I think I mentioned this and I want to keep reminding, is NASA, as well as many space agencies, are providing this data. They have a open science philosophy. So all the data is freely available to anybody on the planet. And then the next slide, the disadvantages of remote sensing is very difficult to obtain high spectral resolution, spatial resolution, temporal resolution, and radiometric resolution all in one instrument. There's always going to be a trade-off. And a lot of planning and thought goes into each of these missions that's launched. And what exactly are the objectives of that mission, and what are the trade-offs going to be? Because there will be trade-offs. Another is there's a large amount of data in a variety of formats. And a problem even 10 years ago, definitely 20 years ago, definitely 30 years ago, we didn't have enough data. And even NASA was charging people to use the data. And there's actually, I was just at a conference in the state of Colorado, and they showed a graph of how much imagery from that Landsat mission that I talked about. And before they made it publicly available, so free, and then after. And the amount of downloads and the amount of use from the imagery after they made it publicly available is marked. It is a huge difference, and how much great science has been able to be achieved. So the problem was before we didn't have enough of the data, and now we're swimming in data, just kind of like we're constantly swimming in information from our smartphones and everything else. We're just in a wash of data. So now what we're doing is we're catching up with the infrastructure, the cloud processing, to be able to handle that voluminous amount of data, to be able to actually pick signals out of the noise and actually, as somebody said earlier, I think it was Jen or John Bolton, how can we actually produce information that we can use instead of just having this sea of data, which doesn't really do us too much good. And another thing is applying satellite data may take require additional processing steps. And so that does take some level of training and understanding. And then also has to be validated. A lot of time, a lot of time for these missions, all of them are spent on calibrating the instruments and then also validating the instruments as well. So a lot of that goes on. And to this day, even after they're in orbit, they're still doing that. So next slide. And then this is just some terminology. Again, you have all these slides and they're all translated. So hopefully you'll go back and review that. Next slide. And then this is contact information. I think somebody mentioned it earlier, but this is the program in which I'm part of. Is called the NASA Applied Remote Sensing Training Program. And we give free trainings online, so they're not in person. Some of them are, like right now, but most of them are online. And we do trainings from air quality to disasters, to agriculture, you name it. and they're all freely available. And even if you didn't take one of the trainings, they're all on YouTube, and all the materials are online, and all the materials are translated to Spanish. So you have access to all this. So if you're interested in learning more about remote sensing in general and very specific applications, if it's water quality, or if it's, assessing water budgets in different river basins, we have all these different trainings that you can go to. So I think that's the last slide here. And what I would recommend